had discovered how snakes had turned their bodies into bioweapons, engineering venoms of staggering diversity. And that diversity keeps evolving as snakes tailor their venom to suit their wide-ranging habitats, including even underwater.
The sea snakes are incredibly venomous snakes. And the reason for this is that in the aquatic environment, they don't have the luxury of tracking their prey. If the prey gets away, that's it. Someone else, like this little ray here, is going to make an easy meal out of it. So they need their incredibly toxic venom in order to make sure that they get their meal.
Sea snakes evolved from land snakes only 30 million years ago, and they're still refining their venom. They prove that snake venom is still adapting. But when did its evolution first begin? When Fry first set out to solve this mystery, it was assumed that venom was a recent innovation. It was all to do with snakes' extraordinary fangs. Fangs are hollow, hypodermic needles through which venom flows under extreme pressure. This is how the fangs of a spitting cobra can propel its venom as far as 8 feet. They're so perfectly engineered to deliver venom that it was assumed fangs and venom had to have evolved together. But when Fry inspected the fangs of modern snakes, he found something intriguing. 3 major groups of snakes had evolved very different fangs.
You've got different lineages that have hollow front fangs, but of very different types, where the vipers, like the American rattlesnakes, swing on hinges and are very long. The cobras are short and fixed, while the stiletto snakes, they pop out sideways.
For Fry, this meant venom must have existed before the different types of fangs. Sure enough, when he and other snake experts across the world traced the evolution of venom back in time, they discovered the first snakes had no fangs, but they did have venom. For Fry, this suggested something strange. Maybe snake venom didn't start with snakes at all. Rather, they'd inherited their venom from an earlier ancestor. Snakes evolved from lizards 100 million years ago. Could they be the source? Fry decided to study them.
But they can be quite tenacious once they latch on. Now, better this than my hand.
Fry's theory went against common wisdom. Out of 5,000 lizard species, only 2 were known to be venomous, and they were considered evolutionary freaks. Fry decided to search for other venomous lizards. He zeroed in on the most ancient lizard species in the world, monitor lizards, such as the Komodo dragon. Komodos are fast ambush predators that can grow to the length of a car and weigh as much as a linebacker. The bites from their serrated teeth result in rampant infection that eventually kills their prey. Scientists had long thought this was caused by bacteria, 80 species of which are known to exist in the Komodo's saliva. But this explanation didn't satisfy Fry.
It never sat right to me about all this stuff about the toxic bacteria and Komodo dragons because, well, bacteria don't work that way. They don't cause rapid bleeding, muscle pain, and neurotoxicity within the first few hours unless it's some sort of escaped bioweapon or the Andromeda strain.
Fry wondered if there might be something other than bacteria triggering toxic effects in Komodo's prey. To find out, he would have to take a closer look. Using a brain scanner, he imaged the head of a Komodo dragon. It was then he found something that had been totally overlooked.
With the Komodo dragon, you can see a very large bulge running the length of the lower jaw. And with our magnetic resonance imaging, which is the same technology that you use to scan a brain to look for cancer, you can see the bulge there. Now, if you look into the beauty of technology, you look within it, you can see a very complex gland arrangement, and that's actually a venom gland.
Fry had discovered a venom gland similar to that of snakes. Might there be other venomous lizards? There was only one way for him to find out.
So to decide what was happening, we ended up going out and collecting as many of these things as we could.
Fry's team swabbed the mouths of hundreds of lizard species for saliva samples. He isolated their active molecules and tested them on animal tissues. The results were remarkable. The molecules broke down the animal's heart muscles and toxified their lungs, the same way as the venom of certain snakes. This wasn't bacteria. This was a slower-acting form of venom. Fry's team eventually found snake venom components in more than 1,500 lizard species. He had rewritten the evolutionary record.
We just started looking at what was actually the chemical composition of the venoms and found that there was several components that were shared between the lizards and the snakes. And this was the final proof that they shared a common venomous ancestor.
It's now thought that snake venom, the snake's deadliest weapon, started its evolutionary journey in ancient lizards, millions of years before the snake itself first appeared. But these were not the first animals to evolve venom. In evolution, useful things tend to evolve more than just once. It's true of jaws, it's true of eyes, and it's true of venom.
Venom's appeared in several different groups of animals all over the world. It's appeared in fishes, in mammals, in insects, all independently. And when it shows up in a group, it stays because it gives them such an advantage over the animals with which they're competing.
A riddle remains, though, about venom. If venom gives such an advantage, why does it exist in only an elite few? Why don't all animals have it? After snakes, scorpions rank as the second deadliest group of animals in the world. They kill, on average, 5,000 people per year, injecting venom into their victims from their tail-borne stingers. Venom has helped scorpions to flourish in harsh desert habitats for more than 300 million years. But for all its advantages, could there be a disadvantage to having venom? That was the question Zia Nassani decided to explore, using one of the world's most toxic scorpions as his test subject.
The species that I work with is called Parabutis transvollicus. It's a butid scorpion, one of the largest scorpions out there.
Nassani studied their lifestyle intensively, their nocturnal hunting patterns, preferred desert habitat, and their use of venom. He found that a scorpion's venom gives it an enormous edge. But what happens when it has used up its supply? Nassani devised an experiment to compare one scorpion armed with a full gland of venom and the other completely drained of its venom. He used a miniature oxygen tank to measure their activity rates and found a startling difference. The milked scorpion used up to 50% more energy than a scorpion with a full supply of venom. Once having deployed its venom, a scorpion's body shows the same signs of extreme fatigue as a marathon runner after a race. Just as an athlete struggles to replenish protein and electrolytes, a depleted scorpion has to devote most of its energy toward remanufacturing its most critical asset.
Venom does have a trade-off, and that is it's not good for multiple uses. You have to use it and then make more. And every time you use it, you have to produce more with your body, and that has an energetic cost.
For the scorpion, there's another disadvantage to venom. After it's used, the animal is effectively defenseless for days.
When their venom is completely depleted, till day 4, they have to be very cautious in their foraging habits because they're susceptible to predation. Also, they have to limit themselves to capturing smaller prey items, so that leaves them at a competitive disadvantage.
These drawbacks may explain why venom is not more common in the animal kingdom. But there's a bigger reason why many other animals haven't evolved venom. Venom needs complex, sophisticated biological engineering to inject it.
In order to have a venom, you need to have a way of delivering it as well. And there's been a lot of different ways that this has been evolved, whether it be the fangs of the spider, the barbs of a stingray, the spines of a stonefish, the spurs of a platypus, etc., etc. Each one has their own unique way of delivering it.
And these customized pieces of hardware suck down even more biological energy, making venom not just a superweapon, but one of the most biologically expensive innovations that animals have ever evolved. Every venomous animal has a dilemma. It's armed with a deadly weapon that's a huge burden to maintain. Each has evolved a perfectly precise method to make venom work for it as efficiently as possible. None more so than the animal that turns its victims into zombies.
My family and I witnessed 3 red lights north in the sky.
This thing just floated across. Venomous insects, ounce